LHC seminar. I'm very happy to welcome Emir Muhammad from LHCb. He's actually still a PhD student at Warwick University and is working there on the measurements of the Z boson mass, which he will also present today. And his PhD will finish in June, I was told. So before he actually worked also on these, but more on in the Higgs sector on 2,4 leptons at the University of Birmingham. And in LHCb, he's also active on improving the simulation submission system and the detector description for simulation. So thank you very much, and the floor is yours.
Right. So let's make a start. So good morning, everyone. So it is a pleasure for me today to talk to you about the first measurement of the Z boson mass with the LHCb detector. But before we go on into discussing the actual analysis and the eventual results, I thought it would be a good idea to go back in time and give a brief historical context on why this analysis is pretty interesting. So back in 1967, Steven Weinberg released this landmark paper, A Model of Leptons, where he is able to show how the electromagnetic force and the weak force are actually unified, and also showed how we can describe how the spontaneous symmetry has been broken using the Higgs mechanism. One of the most important results from this paper is that he's actually able to describe the W and the Z bosons mass. He showed that these two bosons are actually described by three fundamental parameters at tree level, the Higgs expectation value, as well as the two coupling constants, G and G prime. And of course, he also showed how the weak mixing angle is related to the two boson masses. During the time of the paper in 1967, based on the experimental results at that time, he is able to show that the W boson's mass is something bigger than 40 GeV, and the Z boson's mass is something that's bigger than 80 GeV. And by the 1980s, this prediction has been refined so that the Z mass is predicted to be about 90 GeV. This was quite a big problem at that time because there was no colliders that were able to access that energies during the 1980s. So this is where we get to UA1 and UA2, as well as the SPPS collider. So at CERN, the SPPS collider was a collider that collided protons and antiprotons, and there were two experiments, UA1 and UA2, that were able to use those to make measurements. And in these two experiments, they're actually able to discover the Z boson. So here on the left, we can actually see a very nice event display from UA1 showing a Z candidate decaying to two muons. And on the right, we can see a discovery plot from UA2 of how they can see a couple of Z candidates. Now, over the course of the experiment, they refined their measurement, and by the end of the run, they're able to measure the Z boson's mass to be those two values on the slide. And these are the values that are currently in the PDG at the moment. So this is all great. We're able now to measure the Z boson's mass to the tree level, but because it's at tree level, we'd like to go more. We'd like to go into higher precision. This is getting a little bit more complicated because when we want to go into higher precision, we need to start factoring in things like the loop correction. So here we can see the W with the loop corrections here going back into the W. And when we factor in the loop corrections, now it depends on many, many other things like the top mass, the Higgs mass, etc., which gets quite complicated. So a lot of groups have been doing this, and they're able to generate what's called a global electric fit, where they're able to pretty precisely predict the fundamental observables in the electric sector of the standard model. So one such global electric fit is presented here by the HEP group right there. What's nice about the global electric fit is that it is mostly over-constrained, meaning that it is able to provide very precise predictions of certain observables. So for example, the HEP group is able to provide what's known as an indirect prediction of the Z mass, which is the prediction of the Z mass where we take all the experimental observables that are available at that time, except we exclude the direct measurement of the Z boson mass. And we get an indirect prediction of about the precision of about 8.8 MeV. So that's the side of the theorist side, but now we can go look into the experimental background of this, and no experimental background is complete without taking a look at the LEP legacy. So LEP, also known as the Large Electron Positron Collider, was a collider that existed at CERN between 1989 to 2000, and as the name would suggest, it is an electron-positron collider. What's nice about LEP is that they're able to tune it to the Z resonance in the center of mass energy, meaning they're able to collect a large amount of Z bosons, something like 17 million to be exact. So what LEP did is in their Z-mass measurement is they're basically able to access the observables via an energy scan. So if you take a look at the data points on a plot on the right, we can see that the LEP has been tuned to many different center of mass energies, and LEP is able to perform a cross-section measurement. And from this very nice plot that they have right here, they're able to extract the line shape parameters, including the Z-mass. And they've measured the Z-mass to something that's super precise at about 2.1 MeV. But of course, LEP was something in the past. Now we're inside the LHC area, along with many other Hadron colliders. So LEP naturally was designed to be a precision machine, but the LHC was itself designed to be a discovery machine. Which does beg the question, if you're doing it inside a discovery machine, is precision electric possible in the first place? Well, let's take a look at the two differences and the facts between the E plus E minus collider and Hadron colliders like the LHC. At LEP, we typically measure the Z-mass or other observables mainly with a beam energy scan, as you saw before. So the main crux of the analysis in any E plus E minus collider is basically in the understanding of the beam energy calibration. Meanwhile, in the LHC, it gets a little bit more complicated because we're colliding hadrons such as protons in the LHC. So the production mechanism is mainly composed of understanding which partons actually interact. So the best way we can actually measure the Z-mass and access the observable there is mainly looking at the final state kinematics. So that becomes really important. So in Hadron colliders like the LHC, the detector calibration really is the most fundamental crux of the analysis. So those are in Hadron colliders. Let's take a look at what electric measurements have been happening inside Hadron colliders overall. And here I select two important results, one from CDF on the W mass and one on CMS on the W mass as well. So as you may have realized, the W mass really is the main focus of precision measurements in the last few years in Hadron colliders. But I mentioned before again that the detector calibration is the most important part inside any precision electric measurement. And this is clearly shown in both the measurements of the W mass in CDF and CMS, because they both use the Z mass in order to validate the calibration of the momentum response. So on the left, we can see CDF's main momentum measurement plot, where they've essentially calibrated the CDF detector with J size and upsilons, and then eventually performed a Z mass validation measurement, which is shown here on the bottom. And that result has been shown inside the PDG. CMS has also done something similar, where they have calibrated with a J size for the momentum response, and they've performed another similar Z mass-like validation measurement with an achieved position down here. However, CDMS was very much specified that this measurement of the Z mass inside their W mass paper is not yet a fully independent measurement and should not be taken into the world average. But basically, taking a look at these two experiments, it basically showed that it is possible to take a look at the Z mass measurement and being able to perform that measurement. We just need to put in a little bit more work in better understanding the calibration to overall get the first dedicated measurement of it. Which brings us into the experiment of focus today, LHCb. So LHCb is a single-arm forward spectrometer that's located in Pit 8 at CERN and is currently operational. And being a single-arm forward spectrometer, it's unique compared to the other detectors at CERN like ATLAS and CMS, in that in ATLAS and CMS, the tracking region is within ethers of minus 2.5 to 2.5, but LHCb being in the forward region is between 2 and 5. The reason LHCb is set in the forward region is mainly because it's originally designed for B and T physics. However, overall, over the years, after a lot of work into the tools and the measurements, it can now be considered to be somewhat of a general purpose experiment, which is quite exciting. Now, on the right, I have here a plot of the integrated luminosity we measure over the years. And even though this measurement is mainly focused on a portion of the run-2 data, I just want to highlight here that in 2024, we've increased our luminosity and able to gather a lot more. Basically shows that in 2024 alone, we're able to double our run-1 and run-2 statistics. So it's quite interesting to look forward for future results from them as well. So stay tuned for those results. But since we're taking a look at the run-2 detector, run-2 measurements, this is the run-2 detector of the LHCb experiment. And this is mainly composed of a few main parts, mainly the tracking, the PID, and the calorimeter itself. But because to measure the Z mass, we really need to understand the momentum response really well, today I'm mainly going to be focusing on the tracking systems itself. So the tracking system is composed of a few main parts. One of them is taking a look at the run-2 detector's dipole magnet, which is shown in blue here. So this is a warm dipole magnet with a field strength of 4 Tesla meters, and it is done in the vertical polarity. But what's quite nice about the LHCb's dipole magnet is that the polarity is switchable, meaning we're able to switch between the magnet polarity going up and magnet polarity going down, which is going to come in handy for a lot of validation cross-checks. And we have the magnetic field map itself on the plot on there. Now we get into the tracking system itself of the detector, which there are at least 3 of them, which are important for our detector. So the 3 of them are the Velo, the TT, and the T stations. So the Velo is located right here in the front. It is a silicon strip vertex detector, and the Velo actually stands for vertex locator. So as the name suggests, its main job is to measure precisely the location of the vertex itself. After the Velo, there's another set of detectors called the TTs, which are basically just silicon microstrip trackers, and it's able to give us some extra redundant upstream tracking information before the magnet. After the magnet, we get this set of trackers called the T stations, which are composed of 3 layers, and it's mainly composed of 2 subdividing parts. The inner tracker, which is where it sits closest to the beam pipe, is mainly made of the silicon strips, whereas the outer tracker is mainly composed of the straw drift tubes. And you can see the momentum response on the right there, showing the precision of what we can see inside the tracking system, which is quite nice. So those are the tracking detectors we have, but when we want to do measurements, we need actual tracks. So the way that we form tracks inside the LHCb detector is by first performing a Kalman fit to form the tracks inside each of the subdetectors to eventually form a full track. And then we also perform an alignment to make sure that the detector is aligned correctly. And the way that we do the alignment is essentially by reducing the track residuals. What's quite nice in LHCb and what we should celebrate in LHCb is the ability for us to do the alignment in near real time. So at the start of the fill, we perform a detector alignment in the beginning. And as you can see, that information is actually fed here in the green box in the data taking during the software trigger between HLT1 and HLT2. So the alignment runs as we collect the data, which is something that's quite nice to see. Lastly, something important that I should mention in the detector is that we also have the muon stations, which are located in the back, mainly composed of multi-wire proportional counters as well as general electron multipliers. The important part about the muon system is that it really has an excellent muon ID efficiency, giving us a muon ID efficiency of something that's larger than 95%, which is quite exciting to see. That brings us into the entire detector, and using our unique detector, we're actually able to generate a relatively comprehensive electric program. What's quite nice about the electric program is that it is very much in complementary regions compared to other detectors like Atlas and CMS. So we can see the plot here showing how Atlas and CMS are living in the middle region here, whereas LHCb is in the 2 regions on the side. Based on the program we have, we've actually done quite a lot of electric measurements. So for example, in the cross sections, we do ones that are like W to mu nu at 8 TeV, Z to mu mu at 13 TeV, and countless others I won't list, but we've done a lot of cross-checks in different center of mass energies and decay change. And we also have done a lot of work in the precision electric sector. So recently, we were able to measure the W mass with our 2016 data set, and we're also able to measure the leptonic weak mixing angle. I think it came out in the last year. But given that we're able to measure those two observables with a high degree of precision, the question, of course, is if we're able to measure that, can we measure the Z mass? So what does the Z actually look like in the detector? Well, the Z decays basically look like the picture shown before. As I mentioned in the last few slides, we have an excellent muon ID efficiency, so naturally we are most sensitive to the Z to mu mu decay channel. So what the Z looks like is essentially, as shown in the picture, we have Z decaying to 2 muons that are high PT, as you can see in the green tracks right here. And these 2 muons have a combined mass of roughly 91 GeV, and that's what the Z looks like in the LHCb detector. So so that's quite nice. So it means that if you're able to see the Z to mu mu decay chain, we can basically take a look at its dimuon mass spectrum because we're able to reconstruct both muons, which is quite nice. So we can see that the Z is over here, so we can take a look at the peak right here. But this plot also shows us a problem that we need to sort with, because as you can see, if you want to measure the Z mass over here in this peak, we need to be able to calibrate the momentum response of the detector using other dimuon spectrums. which is difficult because in this plot you can see the z is pretty much alone all on this side of the plot and there's nothing around it. So really the main crux of the analysis really becomes being able to transport and calibrate using the lower mass resonance like the J size and the epsilon 1s, and being able to transport that information all the way to the z. And that really is the main crux of the analysis. With that, the analysis strategy for the z to mu mu analysis is that, to repeat, we are very much sensitive with the dimuon mass distribution, and the way that we perform the fit is by comparing the full simulation with the data. We vary the z mass hypothesis by reweighting the full simulation we have generated by LHCb with some generator level events, and I'll get to that in the next few slides. But what's quite nice is that we also have the previous MW and the weak mixing analysis tools, so we can definitely build off those precision electroweak tools to perform our z mass measurements. And as I mentioned before, the main crux of this analysis is being able to understand the detector response and to also essentially control the difference between the data and simulation. This really needs to be well under control. That brings us to the data set and selection that we are using. So the selection itself is relatively quite simple. We only require the signal selection to be z's decaying to 2 muons. We require the muons pseudo-rapidity to be between 2.2 and 4.4. And we also require the muons PT to be above 20 GeV. The muons also need to have been identified muon candidates, which are matched to single muon triggered paths. Because we're also doing a lot of calibration, we also take a look at the quarkonia, so we need to take a look at the quarkonias as well. These are mainly composed of two samples, the epsilon 1s and the J size, both decaying to 2 muons, and we typically use the epsilon 1s to 2 muons as a calibration and the J size as a cross-check. We also require the muons eta to be between 2.2 and 4.4 and the PT to be greater than 5 GeV. Importantly, the data set that we're using is only the 2016 data set, so it's about a third of our full run-2 data set. And based on that data set, we can already get from the selections that we are seeing about 170,000 data events in the Z to mu decay chain. From this, we can actually already perform a very quick, naive statistical uncertainty calculation. So based on the number of events we get after the selection, we can already expect that our statistical uncertainty would be of the order 8 MeV. The simulation plays an important part in our analysis itself. So as I mentioned before, we need to understand the difference between data and simulation. So the simulation is basically the completed events and the detector interactions are actually simulated with Pythia with the LHCb specific tune, as well as Geon4 for the detector interactions, so Pythia and Geon4 respectively. And a variety of models were used to reweight the events to next to leading order accuracy, but we'll get to that later on. So just to quickly mention what the background we're looking at is. This is a very nice plot from the weak mixing paper that came out a few years ago, last year, using the full run-2 data set for the Z to mu decay chain. So while our data set for this measurement is about a third less than that, we can actually see the same features for both this analysis and the previous analysis. And the most important point on this plot is that we are basically background free. We can see that in the Z mass region, the data are roughly at the order of 10 to the 5, whereas the background is roughly at about 10 to the 2. So we are at least 3 orders of magnitude between data and simulation. So we are operating in a background-free region, effectively. So that brings us to the main crux of this analysis, and that is essentially inside the momentum response. So this equation I have right above here is showing the difference between the data and simulation, and they are in the form above, which, as you can guess, is quite complicated. So let me get through each of the terms one by one to better understand where the terms come from. There are two main groups of terms that we really need to worry about inside the momentum response. That is the left term here on the left, which is corresponding to the bias term, and the one on the right corresponding to the smearing term. So the bias term, as you can see from the equation, really has a large effect on the mass bias. So you can already see if we change the value of alpha by a bit, that's going to change what the momentum that we're seeing in the detector, which will then naturally affect the mass that we see. But because it's mainly affecting on the mass bias, it actually has a relatively small effect on the mass resolution, which is quite nice to see. We also have the term on the right, which is corresponding to the smearing terms. And we can see that they are smearing terms because they both depend on these two R values. And these R values are basically just random numbers generated from a Gaussian distribution of mean 0 and standard deviation 1. So because of that, we can already see that this overall smearing term has a relatively small effect on the mass bias, but it does have a large effect on the mass resolution. Let's delve deeper into the actual terms and where they actually come from. So on the bias term, we are mainly interested in the three terms over here, alpha, beta, and delta. Alpha represents the momentum scale, which can be due to something like an incorrect or inaccurate magnetic field map. And what's quite interesting about the alpha term, the momentum scale, is that it can be time and direction dependent. So this is something that we need to be able to correct for. The beta in the middle corresponds to the energy loss term. And the energy loss term basically comes from the uncertainty inside the material budget in the detector, and that is something that we also need to correct for. And lastly, we have the delta here, which is caused by the detector misalignment. And as you can see from the way that the equation is written, this is very much a charge-dependent curvature bias. So you can see how the minus plus and the plus minus interact with each other in the equation. On the right, we also have then the smearing terms, and the one on the left typically comes from the material scattering inside the detector, which we control for. And on the right is also the detector resolution from the inherent resolution of the actual detector itself, where A and B are some functional form of eta, which I won't get into much detail, because as again, the main analysis is primarily focused on understanding the bias terms itself. So this is a big complicated equation that we need to be able to correct for. How do we actually correct for this efficiently? This is done in a 4-step procedure. So we have 4 steps to correct for this, and the first step we do is by performing the correction of the curvature bias. We do this with the pseudo-mass method and using Z events. Then I mentioned that we are using that the alpha is both time and direction dependent, so we need to be able to correct for the mass scale terms right there. So the second step we do is to perform the time-dependent correction with the epsilon 1s events. And then we also do something similar for the direction-dependent correction for the epsilon 1s. Now that the alpha and delta are really well understood and corrected for, then we can finally perform the final generalized momentum smearing, which will eventually then correct for all these 3 parameters, the alpha, the sigma 1, and the sigma 2. And this is by far the most important step inside the momentum calibration. And this is where we all get our final correction before we then move on to using the terms here to measure the mass of the Z boson. So let's go through the steps one by one in detail to show you how we actually perform the correction. As I quickly mentioned before, the misalignments typically lead to the curvature bias. So if there's any misalignments in the T stations, these manifest itself in the momentum response as a charge-dependent curvature bias. So how do we correct for this? Well, let's take a look at the main dimuon mass equation we have here on the left, which shows us the dimuon mass equation where we assume that the muons are massless. But we can see that since this is sensitive to delta, unfortunately the delta we have in the equation down on the bottom left largely cancel out in the above. So we need to do something else. We need an estimator that doesn't cancel in the dimuon mass, so we can see this curvature bias and correct for it in the first place. This is where we go into the pseudomass. So this has been seen and used in D0, but this was further refined in LHCb, and now we have something we call the pseudomass. And the pseudomass really is just an estimator for this mass where we assume we have all of the information from one muon, and we only take the direction information from the other muon. So we can see that these 2 terms represent one of the muons, and the other term, the P over PT, is completely described by the direction of the other muon, which is quite nice to see. But also this shows that we can actually get the pseudomass for both the positive muon and the negative muon. How does this help us? Well, we are able to plot the distribution of the pseudomass for both the positive and negative pseudomasses, and this is an example of what we see in the 2016 data in LHCb with magnet polarity up, where the results come from this pseudomass paper that came out recently by LHCb as well. What's quite important to see here is that a few features are shown. You can see that the positive and negative pseudomass are slightly apart, and this shows us that there is some level of curvature bias that we need to correct for. What's quite nice is that to correct for this curvature bias, all we need to do is we only need to worry about the asymmetry between the positive and negative pseudomass. We don't really need to worry about the absolute value of the pseudomass itself. So we can see this very nice distribution, and we use this to correct for the data. The way we actually correct the data is actually a little bit more subtle. What we do is we correct the asymmetry from the difference between data and simulation to account for the small physics biases that may exist. Now, because we're measuring the Z mass, it is quite important for me to hammer in the fact that this method is mostly unbiased with the Z mass. We can see here by doing a few things. When we take a look at the equation from before, we don't see how this has any dependence with the Z mass. But also, in the way we perform the curvature bias, we're only interested in the asymmetry between a positive and negative pseudomass. So it makes no assumption on what the mass of the Z boson is. To make this even clearer, we actually did the check in the analysis itself. So in the simulation, we varied the mass of the Z boson by about 100 MeV, and this has of the order of 0.3 MeV or 300 keV in the final measurement. So it's very much unbiased, which is quite nice to see. So this is what it looks like. So we can see that to perform the correction, we actually do the correction in bins of eta and phi. So we can take a look at the corrections in the different detector regions. And this is what we correct for in the data. And as you can see from the plot, the corrections are of the order 10 to the minus 4. More details can be found in the standalone pseudomass paper that we recently released about a year ago. So that's nice. So we are able to correct for the charge-dependent curvature biases and the detector misalignment inside the detector itself. What do the results look like when we perform that correction? And that is shown here, where we can see on the left the dimuon distribution of the epsilon 1s before and after the pseudomass has been applied. And on the right, we can see what the data for the Z also looks like before and after the pseudomass has been applied. And you can see that the resolution improves by quite a bit. We also assign a systematic uncertainty of 0.8 MeV to the method itself. The way we do this is by essentially just using the covariance matrix and the statistical uncertainty from the fits from the last slide and propagate that all the way to the final Z fit. And we see that this changes the mass of the Z boson by about 0.8 MeV when we take a look at the statistics from that. Now we can move on. We can move away from the charge-dependent curvature bias and take a look at the other corrections, mainly in the momentum scale, which is one of the most important things we need to control in the Z mass measurement. It's been well reported in LHCb that there is a time-dependent mass scale in LHCb that is something that we need to correct for. And this is most obviously seen in the various papers in LHCb, where we can see that the epsilon 1s mass actually vary as a function of time. But what's quite nice about this is that if we can take a look at the epsilon 1s peak itself, you can then also use the epsilon 1s to extract the line shape parameters. So by extracting the epsilon 1s mass in bins of different 2016 data taking period. And we can actually perform, we can take this and perform the correction to basically correct for any kind of time varying momentum scale uncertainties we see. So yeah, we correct the mass by comparing with the PDG values, and this is what the distribution looks like as a function of data taking period. And because this is something that we see in data, we also correct this in data as well. Next, we perform a direction-dependent momentum scale, similar with how the momentum scale varies as a function of time. It also varies as a function of direction. So we actually also, it's well reported that there's also some localized biases across the detector due to the magnetic fields. And so the way that we correct for this is also by performing essentially a procedure that's very much similar to before. We extract the epsilon 1s mass line shape parameters for each eta and phi bin for both data and simulation, and this is what the plot looks like. We can see that in the simulation it is very much uniform, whereas there is some differences in the data. And what we do here is we correct the simulation to match the data. And then that's how we perform. And so from steps 2 and 3, that is how we are able to correct for both the time and direction-dependent mass scales. That leads us to the final and the most important part of the momentum calibration, which is the final momentum smearing correction itself. As I mentioned before, we are mainly here, at this stage, we're mainly correcting for the alpha, the sigma 1, and sigma 2. And from the plot on the left, you can see that the way we correct for this is by performing a binned chi-squared fit for both data and simulation. So we can see from the plot on the left, there's quite a few interesting features that it might be useful to be looking at. So importantly, after doing a lot of the corrections in the alpha, we can see that the mass scales actually line up really well between both data and the uncorrected simulation. But since we haven't done anything with the resolution, you can see that the resolution inside the simulation is too optimistic. So we need to perform some smearing. And when we perform the final momentum smearing fit, we can see that the simulation really matches really well with the epsilon 1s value. So we can see that data and simulation really match really, really well. So at this point now, everything is well under control. Alpha is now really well under control. We only see a small correction of 0.65 times 10 to the minus 4. And there's also the values for sigma 1, sigma 2. Now, sigma 1 and sigma 2 is worth discussing about in a bit because these two smearing parameters are actually somewhat anti-correlated. But as we mentioned before, there's a very, it doesn't really affect the Z mass. So what we do is we actually allow this Q over P curvature term, the sigma 2. We allow this to float in the final Z mass fit with some multiplicative factor in the final Z mass fit, which allows us to be able to measure the Z mass really precisely. However, because we do float this sigma 2 term, we are not able to measure the Z width at this analysis. So all of that, we can then go into finally looking at all the uncertainties that are relevant for the momentum smearing terms. And as you can see, some of you might have realized that I didn't really speak much about this beta term. This beta term is the energy loss term. And because it's very much correlated with the momentum scale, we then treat this as a systematic instead. To treat this as a systematic, we typically take the default description for the material budget and then vary that by about plus minus 10%, which is what the measured uncertainty of the material budget is. When we propagate this to the final Z mass fit, we eventually see that the size of the detector material description uncertainty is about 2.6 MeV. We can also perform a lot of other uncertainties. So one of the ones we did is the calibration samples. So as you might have seen from the last slide, we calibrated with the epsilon 1s. We can swap this with the J size or another sample of epsilon 1s with the lower PT. And when we perform this uncertainty, we can see that this has a difference of about 2 MeV in the final fit. We also perform the smearing fit to transfer the information from the statistical uncertainty from the smearing fit all the way to the Z, and we see that it gives us a 1.8 MeV in systematic. And we also applied the other uncertainties like the PDG mass over the epsilon 1s, the curvature bias that you've also seen, as well as the QED corrections in the epsilon 1s mass, giving us a total uncertainty of 4.1 MeV. So that's all of the momentum scale all corrected for, and now we can then finally see what we do with the reconstruction efficiencies. So to perform the reconstruction efficiencies, what we do is that the muon trigger, ID, and tracking efficiencies are measured basically both in data and simulation using the standard tag and probe method. This is pretty much very similar to how it was done for the weak, W mass and the weak mixing analysis, so I won't go into too much detail, and the simulation is also corrected with event by event weight basis. This efficiency correction also eventually contributes, it's very small, so it only contributes about 0.1 MeV to the uncertainty, so it's not as important as the momentum scale corrections. So that's all of the data calibrations that we need to do, and now we can finally take a look at how we deal with the theory side of the Z-mass analysis. As a reminder, we use PYTHIA to generate the simulation, but PYTHIA was done in leading order and leading log. So what we actually want to do to measure the Z-mass analysis, to measure the Z-mass is that we need to do a few things. We need to vary the Z-mass itself. We need to be able to treat the Z-gamma interference really well. We need to be able to increase the accuracy of the predictions. And we need to propagate any kind of uncertainties in the theory all the way to the Z-mass. So the solution we do is by essentially reweighting the events themselves. How do we do this? Well, we generate some dimuon mass templates. These are generated from a very special version of Powheg box, which allow us to, which also includes the QED predictions at next to leading order. The electric theory input scheme we use is as shown on the slide, so we use the G Fermi as well as MW and MZ, where we also essentially just generate samples by varying this MZ in the input scheme. And of course, the Z mass was blinded during the analysis to avoid any kind of bias. And using the special version of Powheg, we essentially get a lot of multiple Z mass hypotheses with the correct NLO corrections. Now, importantly, we also need to worry about the other things inside the actual process of the Z itself. So the muons also undergo final state radiation, and in Pauheg, the first photon emission is actually computed exactly by Pauheg, which includes the radiation from initial and final state, as well as the interference. However, the additional final state photon emissions are actually handled by PHOTOS, so we match PHOTOS and Pauheg together to generate the relevant hard cross interaction, as well as the final state photon emissions. Allows us to resum the log-enhanced term. Now, we're actually able to assign an uncertainty under MZ by looking at an alternative prescription for the QED-FSR. So instead of using PHOTOS, we're very much able to swap the description from PHOTOS to Pythia, and that allows us to get an uncertainty of 0.8 MeV. Lastly, we should also take a look at how we deal with the parton density function. So typically, when we perform the Z-mass analysis, we do a central fit with NNPDF 3.1 NLO, as you can see here, as you can see on the plot here. However, the analysis itself is also already set up to be able to swap between NNPDF and other different kinds of PDF sets, such as the ones from the MSHT group and the CTEC group. And we are able to easily swap between the two PDF sets, and that allows us to assign a 0.7 MeV systematic based on that prescription. And the way that we get this 0.7 MeV uncertainty is by essentially just getting the envelope between the three PDF sets. Lastly, you can finally take a look at how we actually measure the Z-mass itself and how we perform the fit. So as you can also see from this plot, we are also taking a look at a binned chi-squared fit, shown on the left. And as I mentioned before, we generated a lot of the Z-mass samples from Pauheg, and we use that to create the full simulation. So you can take a see how the Z-mass simulation distribution varies as we vary the Z-mass hypothesis itself. Gives us a very good fit of a chi-squared of about 44 over 37, and giving us a Z-mass of something, but an uncertainty of about 8.5 MeV, which is very similar to the statistical uncertainty we calculated before. As I mentioned before, we also float this Q over P smearing factor that has a value of 1.25. But the most important thing about this Q over P smearing factor is that it is very much uncorrelated with the Z-mass. So you can see that the correlation between the two terms here are something like 1%, I believe. So there really is a very, very small dependency between MZ and smearing factor, which is completely fine. So that's great. So we're now able to measure the Z-mass using the binned chi-squared fit. These are the summary of all the uncertainties that we have seen. Just to recap, the momentum calibration is by far the most dominant at 4.1 MeV, as well as the other theory uncertainties that we have briefly discussed before, giving us a statistical uncertainty of 8.5 MeV, meaning that our total uncertainty for the Z-mass is 9.5 MeV. Something that also is important to highlight is that this measurement is very much unbiased with the Z-mass itself. As I mentioned before, we typically, most of the calibration is done using the epsilon-1s sample, and the pseudomass we apply in the first step of the momentum calibration does not depend on the Z-mass, as I've described before. Now, of course, before we unblind, we have to do a lot of checks to make sure that the entire analysis is doing really well. So this is basically a nice check of the consistency of the subsamples. What we do here is we split the data set into two regions. So for example, on the line on the top, we can see that we have the magnet polarity. What we do is we split the data set from magnet polarity of up and magnet polarity of down, and see how the results differ, where these show the pulse, which is the difference between the values over their statistical uncertainty. And we've done something like about 20 different divisions. And as you can see, they're all really well statistically behaved. All of them are less than 2 sigma away from each other, and most of them are less than 1 sigma, which is as expected. We also do a few more checks to make sure that everything is all right. We can vary the analysis in various ways, such as by changing the number of bins used, changing the range in the final Z-mass fit, along with other kinds of ranges checks, and all of these have very small effects on the final value. We also do, importantly, a final closure check to make sure that all of the final fits actually work. So both the momentum scale corrections, the momentum smearing fit, as well as the final Z-mass fit, the closure checks have all been tested and they all pass. That leads us finally to the unblinding. So just to summarize, we have the LEP combination, which is very well precisely measured at 2 MeV, and the CDF result from the WMAS paper. as well as the electroweak fit. After everything has been done, we now get permission to unblind. So I am very pleased to announce that the mass of the Z boson has been measured to be 91,184.2 MeV. So that is the final result of the Z mass after unblinding. So we can already see a few things are quite nice here. It is standard model. It agrees with both the experimental results from before, as well as the theory prediction. And an important milestone we have actually received is that we have actually reached the electroweak fit precision itself, which is a really big milestone in electroweak precision measurements. That leads us into the future prospects of the measurements. So LHCb has been able to measure a few things, such as the W mass, the weak mixing angle, and the Z mass itself. All of this has been it's really nice that we're able to measure all three as well. We are also performing future measurements. So the W mass and the Z mass are currently being done with the full run 2 data set that is currently ongoing. We can expect about a statistical uncertainty of about 5 MeV for the Z mass and about 20 MeV for MW. And this program is also well underway for run 3 data. Looking outside LHCb, there's quite a lot of encouraging prospects for the Z mass at LHC. We are, of course, eagerly anticipate the dedicated Z mass results from both ATLAS and CMS. And what's nice about this is that most of the uncertainties between LHCb, ATLAS, and CMS inside the LHC is mostly uncorrelated. So as more and more measurements get by, the LHC average would be eventually going as more measurements come by, the LHC average will eventually go down. So overall, an LHC average could eventually challenge LEP, which is quite exciting to see. That brings us to the summary of the stock. So yes, the Z mass can be measured at LHCb. We measured the Z mass to be 91,184. It's very much consistent with the standard model and previous measurements. And this also presents the first dedicated measurement of the Z mass at the LHC. Thank you very much for your attention.
Thank you very much, and congratulations. The floor is open for questions. From outside in Zoom, please raise your hand, and we start here.
Yes, thanks a lot for this nice result, and congratulations. Maybe a small curiosity.
Sorry.
Small curiosity. Can you explain what do you gain by calibrating with epsilon for the scale instead of psi? Can you explain what do you gain for the momentum calibration by using the epsilon instead of the psi?
Oh, so the reason we use the epsilon is mainly because it is closer in PT to the P's and the PT's to the Z mass, because the J size is something at about, the mass of the J size is about like 3 GeV and epsilon is 9 GeV. So by using the epsilon, we are able to just better extract to the Z mass. But as you can see, the difference between the J size and epsilons, there's not much difference between the final Z mass values.
So I had a follow-up question to that. Why did you have less J size than epsilons in your data set?
So the one of the main things we need in the J size is, even though it has a larger cross-section in general, is that we require the J size to be mostly displaced. So this comes from, for example, J size coming from, for example, the B to J psi Ks. The reason we do this is because also in the hardware level, I believe that we cut really strongly on the PTs of the J size. So that's why we have stricter requirements basically on the J size compared to the epsilon 1s.
This answered Andreas' question. Okay, Josh?
Yeah, so can you go to slide 24?
Okay.
So I think this was where you were showing the functional form of the...
Right, so give me a few seconds. Yes.
Yeah. So can you comment on to what extent and how you've validated the functional form, especially for the bias terms, which are the most important for the mass, in simulation on the one hand and in data on the other hand?
So the way that we validate this is by, we already see like a lot of the cross-checks there, but an important way that we validate this is actually taking a look at using the different samples. As I mentioned before, the J size and the epsilons live in 2 different PT regions. And if we're able to show how the epsilon 1s mass information is sent to the Z and how they differ with the J size who live in the different PT regions, and since they both agree, then that's a really good way to show how it's been well validated.
Yeah, I mean, I think it would be really nice to show a plot, even just in simulation, showing the evolution of the momentum scale as a function of like the generated PT of the muon, and you know, also doing that with some alternate material or magnetic field scenario to just make sure that things are really as well behaved as you think.
Yeah, I think we may have a plot there, but I don't know if it's public yet, so we may have to discuss if those plots itself. But yes, that's a good idea. Thank you.
But if I can ask another question on the calibration. So if you can go to, I think it was slide 36 where you had the breakdown of the calibration uncertainties.
Yeah.
So first of all, can you comment on where the statistical uncertainty of the upsilon fits enters here, and how big is it?
Sorry, when you mean the statistical uncertainty of the upsilons?
Yeah.
Based on the data set we get, right?
Yeah.
That would be this one. So we can see that inside the momentum smearing fit, the uncertainty of the number of statistics come into play when we actually measure the parameters for the alpha, sigma 1, sigma 2, and that's what we vary and move all the way to the z. So that's where the statistics of the U1S come from.
Okay, but where does it enter in that table on slide 36?
Oh, yes, that would be in the smearing fit itself.
Okay, good.
Sorry.
That makes sense. Okay, and then on the material, when you propagate it through the calibration, do you vary the material and then redo the upsilon fit?
Yes.
Okay, good. All right, thank you.
There's a question from the outside by Fabio.
Yeah, thanks a lot. A very nice seminar. It's also very nice to see such a precise measurement. I have a question on slide 42 on your final fit.
Okay, give me 2 seconds. Okay.
Sure. Yeah, one thing I not understood, what is this Q over P smearing factor that you fit at the end? Because in principle, if you have well done your calibration and smearing, you wouldn't need this, right?
Where is it? Nope, I've gone too far, sorry. Yes, so going back, so you mentioned about the Q over P smearing term. That corresponds to basically allowing us to float this sigma 2 parameter down later on in the Z mass itself. So that's what the term actually is. Why we do this is mainly because the two smearing parameters, sigma 1 and sigma 2, are anti-correlated. So a lot of the work done in the Z mass analysis is mainly spent understanding the bias terms itself. So there's quite a lot of control inside the understanding of the momentum response in this part of the equation. However, there was not much done in this part, which then shows up in the momentum smearing fit, because when we take a look at the correlation plot, sigma 1 and sigma 2 are very much anti-correlated. So we can't really be able, we can't independently determine the sigma 2 term without some form of sigma 1. So that's why we have to do this.
But when you do the fit, you already correct sigma 1 from the upsilon, right? So you have a kind of tension between the two, because
there is, yeah.
You get, yeah. So maybe something in the modeling is not fully correct, because you shouldn't get this. It's quite significant, right?
Yes, yeah. So that's why in the analysis we are not able to measure the Z width itself. But as we can see from the But as you can see from the results here, the correlation between the smearing factor and the Z mass is really, really small. So we are able to measure the Z mass, but not the width at the same time.
Yeah. Okay, thank you.
Sure.
Andreas. Yeah.
Yeah, thanks. So actually, very nice to see this result. I wanted to ask about the variation that you showed towards the end when you take subsets of the data. I was curious, for some of these orthogonal samples, the variation goes to the same side. So is that not worrisome? I think, it's mostly about plus and minus charge.
I mean, they mostly look statistically all right. So we had a lot of checks on this during the analysis stage, and it really is mainly a statistical fluctuation. So we just got unlucky on that. And within the review as well, we found that there was no issues between, there was no important biases that we've unaccounted for. So these are mainly statistical. So I think we just got unlucky with some of them.
Okay. No, I realize now that it's mostly about flipping the charge. Yeah, okay. The other thing I really didn't understand was treatment of the alpha parameter, which you introduced as momentum scale, and at the end of the talk you also treated it that way, but at some point you said you're also using it as a smearing parameter.
I guess this slide is more of the momentum calibration in general. So it's really a bias term, but in this stage of the fit, we do correct for the bias and the smearing terms like simultaneously. So that might be why. But it very much is a bias term that we correct.
Okay, so here you determine it, but then later you determine it again as a function of time, and you correct the simulation using this alpha term.
Yeah, so what we do here is we do like a lot of the calibration. So in the time varying momentum scale and the direction dependent scale, we perform the correction for the alpha, and that's like really well known by now. So alpha is very, very well measured, very, very well calibrated from the first two terms. The reason we also have to treat the alpha in this stage is mainly because there is a small correlation between alpha and sigma 1 and sigma 2. So in the fit, actually, when we fix sigma 1 and sigma 2, we know in this fit, the alpha eventually goes to 0. So we can see that we don't need to calibrate that again unless we have to start worrying about the smearing terms. So that's why.
I was curious, you didn't say when you looked at the eta phi plot where you show the departures of the data with respect to the average.
This one?
No, the eta phi map, there were 16 bins or so.
Oh, this one.
I was curious, is there a pattern as a function of eta or phi?
This is mainly due to like so basically the what's the word? Where the terms actually come from, like why the alpha, this alpha in this case actually exists, is mainly from the magnetic field map itself. And at the level of precision we want, it's quite difficult to get to the level of precision we want. So we have to perform this direction-dependent momentum scale. So the features are mainly coming from the small inaccuracies and the residuals inside the magnetic field map itself. So, yes.
I mean, I guess Andrea's question is here. How the binning assignment is, and if you see a phi modulation, or how did you order the bins?
Sorry, my bad. The bins are just we just take let's use this one as an example. So so basically what we do is we basically just say bin 1 is like something in this range, bin 1, 2, 3, 4, 5, 6, 7, 8. So it's more like a flattened index of eta and phi, where we have the eta between, I believe it's 2.2 to 4.4, and the phi between minus pi to pi. So we just split that into 4 regions of eta and 4 regions of phi, and then we flatten that index. So it is, that's how the bins are assigned.
You had a question? Or no? Yeah, please.
Yeah. Well, first off, thanks for the nice talk. Really nice result and well presented.
Thank you.
First one, maybe quick question on the calibration. You showed the summary of all the uncertainties for the upsilon fit. Do you have the same summary for the J-psi fit?
No, we don't have that.
But I guess a kind of related question would be, I mean, you said that you prefer the upsilon because it's closer in mass to the Z. But I mean, I'm wondering if this is kind of just a feeling, or if there are hard numbers to support that. Because it seems that if your parameterization is fully robust, then you don't need this kind of feeling approach. And you also have the fact that the mass of the upsilon uncertainty itself is kind of relevant here, and it's much smaller for the J-psi.
Exactly. Another reason we also use the upsilon is because, as we can see from the data set, we actually do have more events for the upsilon.
But if I see this table here, is there any number, if I saw it for the J-psi, is there any number that's going to tell me, oh yeah, I should use the upsilon?
When we see, we actually did like a smaller check as well, but we believe that if I remember correctly, the numbers were like slightly bigger for when we just use the J size. So the epsilon 1s gives us actually better uncertainties.
Okay, thanks. And then the next thing I wanted to ask about is the statistical treatment. Maybe you could go into a little bit more detail about it. I guess that it's chi-squared fit.
Yes,
you're not profiling uncertainties, etc.
No, it's just a simple chi-squared fit.
So then when you show this summary of the pools, are these ratios with respect to the uncertainty in that parameter? So then if I see a 2 sigma pool from the isolation, for example, that would only correspond to like a 1 MeV shift in the mass?
Something like that, yeah. So it's mainly on that particular fit itself.
Okay, thanks.
There's a question from Pascal from the outside.
Yes, thank you. First, thank you very much for this very clear talk and explanations on the systematics. Also, I have a naive question. When you discuss at great detail the momentum scale, but there is one thing which you didn't discuss at all is that is the length scale, because in the mass is directly proportional to theta, which is essentially given by the transverse size of the detector, and you need to know it by 10 to the 4. Did you discuss that, or is it so easy that you don't have to discuss that?
So I guess what you mean with the length scale, you mean like the length scale of the detector, like if it's changing in the Z, is that right?
Not in Z, in transverse size, because the mass is proportional to theta, essentially, to the opening angle between the two particles.
Well, I didn't really discuss this, but the charge-dependent curvature bias also like allows for like misalignments not only in the transverse plane but also in like many different shifts. So the charge-dependent curvature bias should be able to account for the differences in those length scales as well. So, yeah, I think more detail can be found inside the pseudomass paper. So there's the method paper itself here as well as the final result here. So I think there should be more detail on how this curvature bias allows us to correct for length scales such as that.
Okay.
Josh?
So two related questions on the overall momentum scale. So can you maybe go back to the plot where you were showing the eta phi regions?
This one?
No, the biases as a function of the, yes. So can you comment on what the a priori accuracy is expected to be for the field map which you're using in the reconstruction?
I believe like in the relevant scale of like alpha, it's like something like before this, but after the previous correction, something like 3 × 10 to the minus 4, I believe.
Okay, and that's based on the precision of like the mapping done with Hall probes, or? Okay.
Yes, although I wonder if someone more knowledgeable in that can comment, but that's from my understanding, yes.
Okay. Then related, sorry.
Maybe directly.
Yeah, I could comment that indeed it is also checked on the masses of the very low, the known particles at low mass. So this is how it is also checked and calibrated. Not used directly in this measurement, but to get the scale that Amy mentioned.
Yeah. So then related, if you can show the time dependence. Is there some idea for what the origin of this is?
Yes. I wonder if I've linked I think I've linked the paper here by one of our colleagues who did the momentum scale for something like this. But essentially, the reason the shape exists is because, as I mentioned before, the magnet's polarity can be shifted up and down, so in between fills. So basically, we don't have the corresponding plot here, but in that paper you can see how this particular region, when it floats up, is when the magnet's polarity is up, and then when it goes down, it's when it goes down. That's mainly because the magnetic field itself causes a shift inside the detector, and that's how the time-dependent scale.
But this is related to the stability of the current in the coil, or it's related to hysteresis effects, or?
I'm not entirely sure. But these are basically just caused by from what I understand, the magnetic field, when we flip the sign and change the current, then the detectors actually moves. But I wonder if there's anyone who is a detector expert can comment on that. But yeah, that's how it appears in this analysis.
And maybe I comment, indeed, it's the magnetic field to some extent, but it's the alignment in general, so the detector stability over time.
And there's a question by Emilia from outside.
Yes, thank you for the very nice results. I had actually also a question on this time dependence of the momentum scale. So so you have more bins actually for the time dependence and then for the eta phi, but the variations are not so large. I mean, I can see some trends, but they are not so large. So yeah, I just wanted to hear a bit more about this time dependence and why you have so many bins.
Well, the reason we have the number of bins is basically they just account for the different runs we have inside the detector. So inside, we have basically a plot of how many events we actually have as a function of LHCb runs. So we mainly do variable binning to make sure that the number of statistics is roughly the same. And we found out that this was a nice, a nice compromise in the number of bins we have as well as the number of events we actually see. So yeah. Yeah.
Okay, so maybe the last question here.
No, this is just a quick follow-up on that. How often do you switch the polarity in LHCb? Is this something that happens a lot, or is just like a rare special run?
I believe it's in a few months, but I guess at least in 2024, I guess I don't know the answer in the recent run 3, unfortunately.
Oh, could
but
it
in
make
run 2, and in 2016, it's, how do I describe this? This section, which is like the first half of the year-ish, is in magnet polarity up, and then you swap it down for the other half. But yeah.
Maybe it would make sense to bin the plot corresponding to the polarity switches?
It would be, but then the number of events we have would be different, so the statistical uncertainty would be semi-different as well. But they don't really switch as much, so it's not something we need to bin as finely as we need to.
Any last comments or remarks? Okay, then thank you very much again.